All right, so welcome to our 23rd lecture in this course on algebraic topology. We're going to carry on from what we were talking about last time, knots and surfaces. So today we're going to talk about the connection between surfaces and knots. And we can start off with the trefoil knot here. And here I've trying to represent the trefoil knot as the boundary of a two-dimensional surface. I'm sort of filling in the spaces between two different strands of the trefoil knot. So the trefoil is the boundary of a surface, well, a surface, not a regular surface, but a surface with boundary. And today we're going to talk about surfaces with boundary. We're going to sort of enlarge our point of view to include them and be able to talk about the relationship with their boundary knots. So here I've tried to make a picture that illustrates this. The actual surface that's happening here is a Mobius band with 3 half twists in it. Okay, there's 3 half twists, and I've put a knot all the way around the edge. This green strip, it's one continuous strip around the edge. Okay, it's a Mobius band with 3 twists. And now what I'm going to do is I'm going to take away the surface, and hopefully what's inside will be a trefoil knot. Okay, so I'm going to just remove the surface from the boundary. Okay, what do we get? That's a bit twisted, but does it look like a trefoil? Well, if you ignore this thing down here, it's a little bit twisted, but all right, so that's interesting, but if you took a much more complicated knot and tried to imagine how we can do the same thing for a more complicated knot, can we find a surface that has an arbitrary knot as its boundary? That seems like a very complicated problem. And it's kind of remarkable that in the 30s, Seifert proved that every knot can be represented as the boundary of an orientable surface. An orientable surface with boundary. So I should tell you what is a surface with boundary. Well, it means a space in which every point looks like either having a disk neighborhood, like the ones we've already been talking about. So there's a point. Every point has a neighborhood like that. Or every point has a neighborhood that's a half disk with a point lying on the boundary. So it's more general than a surface. It's two-dimensional, but there's also the possibility of being like on the edge of a page. So a page is a surface with boundary. Points like this have disk neighborhoods. Points out here have neighborhoods which are like this. So for example, one way of getting this is just to take an ordinary surface and cut out some disks from the surface. Get your jigsaw and cut out part of the surface. Then what's left is going to be a surface with boundary. And it's orientable when it's orientable in the usual fashion, whether it's possible to give a consistent notion of clockwise or counterclockwise all across the surface. So Seifert's theorem is not of this kind, because this kind used a Mobius band. This example used a Mobius band, which was non-orientable. Seifert said we can actually do this with an orientable surface with boundary, and more remarkably, he gave a rather simple procedure for doing so. And here is his relatively simple procedure. I'll illustrate it for the case of the trefoil. We get something different from what we started off with. So here's the steps. So step one is to orient the knot. Let's take a trefoil. And we'll orient it. So at each crossing, we're going to do something. So the second step is that we're going to trace the knot and at each crossing change to the other strand. Still in the same direction. So let's say we start here, for example. So I'm going to start at X, and I'm going to trace the knot, like here, until I get to this crossing here. There are two strands crossing here. There's that strand that we're on, and there's the other strand. And we're just going to go from here to the other strand. So we're going to just sort of rather abruptly change direction. Okay? And now we're over here, and we're going to carry on. So we go all the way around here till we get to this strand here, this crossing here rather, where there are two strands. There's the strand that we're on, and there's the other one, and we're just going to cross over to the other strand there as well. So make another turn like this. And now we're over here. We're going to carry on like this until we get back to that crossing again. Again, we're going to turn back onto the first strand that we were on. Be over here somewhere, I suppose. So we're back to where we started. And we haven't traversed everything. We've in fact only gone around this part of it. All right, so now what we do is we continue. So we choose another point, let's say Y. And we do the same thing for that. We head off in the direction Y, head off in that direction until we get to the crossing, and then we have to change to the other strand. It means we're just going to go like this. And then here we change, go back to that. So over here, we've gone from here, and then we've gone like this, and like this, and like this. So we end up getting a bunch of circles. Now for our third step, we create disjoint disks with these, they're called Seifert circles. As boundaries. So we have one disk that looks sort of like this, and maybe another disk that looks like this. And we put disks on each of those circles, and we may as well separate the circles a little bit to be able to do that. So we'll think of one, say, as lying in a plane, and another one as lying in another plane above it. So there's now one disk with one of our circles, our bigger one, and another disk with our other circle on top. Now we can still sort of remember that, in fact, these disks are sort of connected in some way. There's that point there and that point there really ought to be connected. And there's a point over here and another point over here which really ought to be connected. And a point over here and another point over here which really ought to be connected. Those are the points that correspond to the crossings of the original diagram. Now in our fourth step, we're going to join the disks together at the previous crossings. The previous crossing locations by twisted rectangles, or twisted rectangular bands. Bands, each with a half twist. Each with a half twist, following the original crossing. Okay, so how are we going to do that? So, let's have a look at just at this point here. So this point and this point of the two disks corresponds back in the original picture to this crossing right here. And at this crossing right here, we originally had, if I first draw that again, we had going like this, I believe. Yes. Okay. So we're going to use that orientation to glue essentially this disk to this disk via a band. Via a band just like, say, this one. If you imagine this band, there's a disk up here and there's a disk down there, and we're going to attach the two disks by this band. but we're going to put a twist into the band. And the twist is going to be, well, it's either going to be in this direction or it's going to be in this direction. And in this direction, it would correspond to this edge going over the other one. It's a bit easier if it's a bit longer. So if it was like this, it would correspond to this right edge going over the other one. And if it was the other way, it would be this way. So we use that twisted, in this case, a twisted one like this, to join these two circles at that point there. So I'll draw that like this. Here's the band that we're going to use. I'll draw it like this. That's a rectangular band that's twisted. And I'm going to do the same thing at the other crossings. There are two other crossings. Maybe I'll move them a little bit over here so I can see better what's going on. So over here, they're all in the same direction. And over here also. Okay, so actually this band should actually be more around should be sort of, these three should be sort of symmetrically located, but I'm just putting them here so you can see very clearly what they look like. And now if you sort of look down on this and you trace the boundary of this surface now. So the surface consists of this disk down here, this disk up here, together with these three bands. If you trace the boundary of this disk, you'll see that you're just tracing it over the original trefoil knot. It's very cleverly designed so that the boundary is the original trefoil knot. And a little bit of thinking shows that this surface is orientable. And it's called a Seifert surface. A Seifert surface of the original knot. Well, it's a Seifert surface of the original knot because it depends on the planar diagram that we used.
So how come you can't interpret avoid this band?
So, say again?
Why? Sorry, the bit band being oriented.
Yeah, so if you imagine choosing an orientation there, all right, so that disk is oriented that way, and then you could just slide that orientation up here, and you would get an orientation which would be in the opposite direction up on that top disk. But now it's consistent. That's a consistent orientation for the entire surface. So just as another example, we could also do this with, say, a square knot. Okay, if you did it with a square knot, then the first thing, well, you could orient it first, let's say in that direction, something like this. And then you would end up getting, at the next stage, 3 Seifert circles, roughly like this, with 6 crossing points. So there'd be a crossing here, and a crossing here, and here, and here, and sort of in the middle. And so you would end up getting 3 disks and 6 bands. Let's just introduce a little bit of notation to help us understand what kind of surfaces these are, these surfaces with boundaries that are coming up. So some notation. So for example, if we start off with just a sphere and we have a single hole in it, we've taken a disk out. So a sphere with a hole drilled in it. Well, this is homeomorphic to just a disk. You just can flatten out the sphere and you get a disk. The hole that you've drawn becomes the boundary of the disk. So we could say we could introduce this notation, d bar for closed disk. Okay. And if we have, if M is any two-dimensional surface, and we form M connected to some d bar, then what does that mean? It means that we're going to connect the sphere with a hole to M. The result of that is going to be the original M with a hole in it. Now, it gets a little bit confusing, though, because you might say, well, this is a hole. When we used to call this a torus with one hole. And if we call this a hole, too, then it becomes a little bit unclear whether we're talking about holes meaning this or this. So for that reason, sometimes this kind of hole, where somebody's actually drilled out a disk of a surface, is called instead a cuff. As in the cuff of a shirt. And you can just imagine having extending the sides of that hole out so that it's like the cuff of a shirt coming out. So for another example, if you're wearing a sweater, an ordinary sweater, pullover, then that's going to be a disk with 4 holes, right? The arms are 2 holes. There's a hole where your neck is. There's a hole where the waist is. And we could write it with this notation as d bar plus d bar plus d bar plus d bar. Or maybe more economically, simply as 4 d bar. So now let's ask the question, what happens to the Euler number of a surface if you add a cuff? Because the Euler number was really the useful invariant that allows us to tell us what is what. Okay, so we want to extend the idea of an Euler number to surfaces with a boundary, but that's no different than what we've been doing. So the question is, what happens to the Euler number chi if you add a cuff? So suppose we have some surface M and it has Euler characteristic chi. And suppose that it's already divided up into lots of little polygonal pieces in our usual way. And we're gonna drill a hole. So we might as well drill a hole in the middle of one of our polygonal pieces. And what does drilling a hole involve? We're adding a cuff. Well, we choose a certain number of vertices on that hole, maybe say 3 vertices. And then there'll be 3 new edges as well. So the number of vertices is going to go to vertices plus 3 in this case. The number of faces is not going to change because I'm cutting something out. What happens to the number of edges? Well, as it stands, if I just cut out this hole like that, it's not actually a polygonal combinatorial surface the way we've been defining it. Because what's left over from this polygon is not a polygonal piece. It's like an annular piece. To get an honest decomposition, we should make one more cut, say that one there. Now, the piece that's left over is actually an honest polygon. So we've actually added 3 plus 1 edge. The 3 could be anything here. And so the Euler characteristic goes to, so if you take this minus this plus this, the net effect is this plus 1 decreases the Euler number by 1. So chi goes to chi minus 1. So adding a cuff reduces the Euler number by 1. So each cuff reduces chi by 1. So we could make a kind of a list. We could sort of say that if we have a sphere with k holes, or k cuffs rather, now, then the Euler characteristic is going to be 2, the original Euler characteristic of the sphere, minus k. If we have an n-hole torus with k cuffs, well, the Euler characteristic of an n-hole torus is 2 minus 2n. And then adding k more cuffs, we have to subtract k. And if we have n cross caps, or n cross cap surface with k cuffs, then the Euler characteristic is, well, remember it's 2 minus n for the n cross caps, and so we need to subtract another k from that. And this is a list of the surfaces with boundary, because if you have an arbitrary surface with boundary and you glue the boundary disks back on, then you get an ordinary surface, which is on our list. And then you take the disks back out. It means you've got one of our original surfaces that we know all about with a certain number of cuffs. So it's an immediate proof that a sort of a classification of surfaces with boundary is really not much more. It's just an ordinary surface with a certain number of cuffs, and it's something on this list. In particular, all the Seifert surfaces that we can get have to be on this list.
But they can't be the last one.
They can't be cross-capped.
They can't be cross-capped.
They can't be cross-caps, yes. The Seifert surfaces are actually all orientable, so they're going to be essentially n-hole torus with k cuffs. This is a sort of a special case of this, right? If you think of n equals 0, that's really this one here. So this is really, these are the kind of Seifert surfaces that appear. So to finish our analysis with the Seifert surfaces, we should just say a little bit about what is the Euler characteristic of a Seifert surface in terms of the number of disks and number of bands that you are used to create it. So suppose we have a Seifert surface with d disks let's say with D disks and B bands. Okay, let me do a simple illustration of that. Suppose we just start off with 2 disks, and we just look at the first step of making that trefoil. What's the Euler number of a disk? Right, if just 1, because let's say you have 3 vertices for the sake of argument, so 3 vertices, 3 edges, 1 face. So the Euler number of a disk is 1. The Euler number of this disk is 1. All right, so now let's just suppose that we have two edges, 2 vertices right here, which are going to be conveniently joined to 2 vertices down here via a band. So when we do connect them with a band, what happens to the Euler number? So here's our band. We haven't introduced any more vertices to make that band. We're using these 2 vertices here and these 2 vertices. We've introduced 1 more edge, 1 more edge, 2 more edges we've introduced, and of course that 1 more face. So we've introduced 2 more edges and 1 more face. 2 more edges and 1 more face. That means that the Euler characteristic has gone down by 1. So the band lowers chi by 1. So in the case of the trefoil, we had 2 disks and 3 bands. So the Euler number of the Seifert surface was equal to 1 plus 1, which is 2, minus 1 for every band, minus 3, so minus 1. Yeah, so when we originally, these 2 disks themselves have an Euler characteristic 2, adding 1 band brings it down to 1, adding another band brings it down to 0, adding the 3rd band brings it down to minus 1. So the Euler characteristic of the Seifert surface is minus 1. And so where is it on our list? It's got to be on our list. In fact, it's got to be one of these. So we can figure out what it is because we know its Euler characteristic. And we know how many holes it has, or how many cuffs it has. How many cuffs does it have? It only has 1 cuff because the boundary is the single knot. This boundary of this surface is the original knot that we started, and that's just a circle. So this Seifert surface has only 1 cuff. And so it is so the Seifert surface must have Euler characteristic equals 2 minus 2n minus k, where k equals 1. And that's got to be equal to minus 1 because we've computed it in terms of the number of disks and bands. So we get the equation 2 minus 2n minus 1 equals minus 1. And therefore n equals 1. And so therefore the Seifert surface is a torus with a cuff. That's what this thing is. It's another picture of it in more standard form. So somewhat more generally, let me add to this thing here, if the Seifert surface has D disks and B bands, then its Euler characteristic is each disk contributes 1, so there's going to be D of them. Each band contributes minus 1, so D minus B. And this D minus B has got to then be matched with this one here. So that's going to be equal to 2 minus 2n minus 1. And that's telling you what the n is, the genus, in terms of the number of disks and the number of bands. N is called the genus of the knot. So problem 25. Determine the Seifert surfaces associated to our planar, our knot diagrams for A, the figure 8 knot, and B, the gingerbread man knot. All right, so that finishes our introductory little tour into knot theory. I might say a little bit more about that later in the course. Next time, we're going to introduce a very important algebraic invariant in algebraic topology, the fundamental group of the surface. So I'll see you then.